First of all, I would like to thank all of the participants and the organizers of the conference to giving me such a nice opportunity to represent my work in this conference. So without wasting any further time, let me start the presentation. So the title of the presentation is self-explanatory, that the development of graphene-based flexible thermocouples for wearable as well as for other applications. So this is the outline what I'm going to represent today. First, I'm going to represent the introduction and the working principle of this type of sensor, and what is the basic thing that that is important for this type of sensors, like Seebeck coefficient overview. And after that, why we choose GNP and PVDF type of composites to making this type of sensors. And after that, the measurements and measurement setups, what we did for taking different type of measurements of this sensor. And in the last, I will discuss about the results and discussions. So first of all, I will like to represent the importance of thermocouples, how they are important in different type of industries like aerospace, automotive industries, and other type of manufacturing industries, because where the temperature is a critical parameter for the measurements. But with the other type of thermocouple which are presently in the market and which are peoples are developing, the problem with this type of thermocouples are sophisticated material preparation, microprocessing technologies, and time consumption, corrosion, chemical stability, and the placement on complex geometries, and definitely the development cost. So the thermocouple based on graphene nanoplatelets and polyvinylidene fluoride offers an alternative to the traditional thermocouples in terms of their flexibility and their lightness and their corrosion properties and things like that. So in this presentation, I'm explaining the development, features, and advantages of this type of thermocouples and their comparison with the commercial K-type thermocouples. So normal thermocouple are consist of two different type of materials, and when we combine the one side of these materials to making a junction and remains open the other end of this type of materials, and when we hit the junction, they will produce a voltage potential difference across the other side of this type of materials, and this can be calculated by using the following formula. So delta V is the potential difference which is generated across the second side of these materials, and the delta T is the temperature difference which is creating on the junction and the other side of the material. So normally the materials with the high absolute Seebeck coefficient are preferred for making this type of thermocouples because they generate higher voltages and with respect to the applied temperature gradient. So we can look with the relative Seebeck coefficient. Here is the table of different metals and their corresponding Seebeck coefficients. If we want to make a good thermocouple, then we have to take a combination that making a large difference between their Seebeck coefficients. We can take the example like antimony and bismuth are the two materials that if we combine both of them, then we can get approximately 119 microvolt per Kelvin difference. So this is a good combination for making this type of thermocouple. In this slide, we can look that the semiconductors has a large Seebeck coefficient as compared to the metals, but there are some problems with creating the thermocouples with the semiconductors. And on the second table, we can look that the different type of thermocouples, and our main focus is the K type of thermocouples in our presentation. The comparison which we are going to make with our thermocouple. So why we choose GNP and PVDF composites for the thermocouple? Because the PVDF is a material with excellent pyroelectric type of coefficient, and its chemical resistance and its thermal properties, and of course its mechanical strength. And secondly, the GNP to improve the conductivity of our PVDF. So and other properties like its mechanical strength, its conductivity, and much more. So here is the method how we prepared our this type of thermocouple. First of all, we took the commercially available graphite intercalation compound, and after that we took the PVDF and dissolved it with appropriate solvent, or you can take any type of appropriate solvent, you can dissolve in it. And a GNP and a PVDF mixture and then deposited on a fabric like the commercial fabric and casted it on different type of fabrics. And after that, we cut this fabrics into 36 by 4 mm pieces and joined them together by using silver epoxy. So after that, we took the measurement, two different type of measurement, the DC electrical measurements by taking 2 centimeter by 2 centimeter sample and by using a 4 probe method to find out the conductivity of our sample, and by using the second setup for finding out the Seebeck coefficient measurement for our sample. The whole setup was consist of a Peltier module that which can produce a temperature range of from 0 to 80 centigrade, and the applied voltage was 5 volt, and for the reference signal we took a K-type thermocouple sensor for taking the reference temperature which we are applying through Peltier module. So here is the open circuit measurements. What shows us that the PVDF and GNP based thermocouple is exactly following the same trend and same linearity that of the commercially available thermocouple. And the K-type thermocouple, commercially K-type thermocouple has the output of 40 microvolt per Kelvin, and ours was 33.9 microvolt per Kelvin. And they are following the exact trend. Secondly, we observed that the trend for in the time response, that the trend was similar like the thermocouple, the commercial thermocouple, and the repetition cycle. Exactly, it is returning to its point that where it started from, and we took 2 measurements for this one to see the repetition cycle. And here is the time response of both sensor of commercial and our sensor, that approximately they are following the same response time. So this shows that it is close enough to use this type of sensors. So why we consider this type of sensors? Because they are cost effective and they are commercially chemically stable and corrosion resistant, and can be used as an alternative to that of commercial thermocouple. Where, as we know that we saw in the previous slide, that the output of our sensor is approximately 33.9 microvolt per Kelvin. That is approximately close to commercial sensors. So thank you for the presentation, and if you have any questions, then I can answer them.